So the word system is pretty general, but it does have kind of a specific meaning within mathematics. So it's a combination of inputs and a process. You have to have both of those things. The process is going to get done to the inputs repeatedly. When you have those two things, you have a system. For example, start with any real number you like. The real numbers are going to be the inputs, and you're going to square root it over and over again. That's the process. You can keep square rooting a number over and over again, right? Here's a second example. Start with any real number you like, and then we have a two-part process. Add 4 and divide by 2 over and over again. So if I start with 8, I have to do the two-step process to 8 to get the next number. So this is really important. The next number isn't 12. You have to add 4 and then divide by 2. So the next number is 6. And then you add 4 and you divide by 2 to get 5. Add 4, divide by 2. And you can keep going as long as you like. Here's kind of a complicated real-world example, which is weather forecasting. The inputs here are kind of complicated, right? Depending on which computer model you're using. You would put in stuff like temperature at different places, barometric pressure, altitude, precipitation. They're all different kinds of things that the computer might want from you. Then what the computer does is its own process, its own program, and then it predicts the weather in time increments. If you've ever looked at a weather forecast by hour, you've seen how this comes out. It can spit out a forecast for every single hour. Well, the reality is the computer uses its own prediction for the weather 1 hour from now to do a prediction for 2 hours from now. So those are systems. Now, a system may or may not show the quality of chaos, which is where small differences in input, little teeny tiny difference in input, will drastically and unpredictably change the output. It does not mean chaos and mayhem. We have no idea what's going to happen. It means big, unpredictable changes when we only change the input a little bit. So back to this example of taking real numbers and square rooting them repeatedly. If I were to start with 10 or 11, they're, I guess, relatively close. And then I plug these numbers into my calculator and I hit the square root key over and over again. Even when I square root once, the numbers were 1 unit apart and now they're like 0.2 apart. And the more times that I square root these numbers, the closer they get together. Now, this is just one example. You could pick any two examples of numbers that you like. You could pick 1,000 and 1,001. And the more you square root those numbers, the closer together they're going to get. And so this is sort of like the opposite of chaos. There definitely is no chaos here. Here's a different kind of system that we can do math problems on that actually does show chaos, which is pretty cool. The initial input is where you pick some point on that red diagonal line, any point that you like. So you only get to make that one choice. And then the process is a two-step process again. You move vertical to the V and horizontal to the diagonal. So for example, if I were to start at about, I don't know what that is, 0.08 or 0.1 comma 0.1. And if I were to do the process to this point over and over again, I would move up to the V and over to the diagonal, up to the V and over to the diagonal. So you might be looking at 4 line segments, but this is actually 2 iterations of the process, right? Here's that third iteration. And a fourth iteration is a much smaller movement. 5 iterations. In fact, you can go as far as you like and make this really frilly cobweb plot, basically. So the big question, does the system show the quality of chaos? What does it mean to show that it has or does not have chaos? What we have to do is we have to run a test, 2 different tests. We're going to change the input just a little teeny tiny bit. We're going to scooch our input point. And then if there's chaos, we're going to see very different cobweb plots. So what I am going to do is start with 0.401, 0.401, and 0.402, 0.402. That's a very small change, right? And in fact, with 2 iterations of the cobweb plot process, I can actually see a little bit of a difference in the cobweb plots, but there's not a very big difference at all. And here's 4 iterations of the cobweb plots, 6 iterations of the cobweb plots, 9 iterations of the cobweb plots. At this point, The points are nowhere near each other. The left plot is like cycling around that little intersection point. The right plot doesn't even know where it's going. So things have gone off the rails completely. We only started 1/1000th of a point away, and even after only 9 iterations, these pictures look completely different. So this is sort of a visualization of what chaos in a system can look like.